For decades, black holes have captured the imagination of scientists and the public alike. These mysterious objects possess gravity so powerful that nothing, not even light, can escape once it crosses the boundary known as the event horizon. Black holes are formed when massive stars collapse under their own gravity at the end of their lives, compressing matter into an incredibly dense point called a singularity. But what if there exists something that behaves in the exact opposite way? What if there were objects that nothing could enter, but from which matter and energy could only emerge? In theoretical physics, such objects are called white holes. A white hole is essentially the mirror image of a black hole. While black holes pull everything inward, white holes would push everything outward. According to mathematics of general relativity, the same equations that describe black holes also allow the existence of white holes. In fact, when physicists first explored the solutions to Einstein's equations in the early 20th century, they realized that the equations naturally produced a time-reverse version of black holes. In a black hole, matter falls inward and cannot escape. In a white hole, matter would be violently expelled, and nothing could ever cross the boundary inward. The idea sounds strange, but the mathematics is surprisingly consistent. In theory, a white hole would appear as a region of space where matter and energy erupt outward from an event horizon. From the outside, it might resemble a cosmic explosion that never stops. Unlike black holes, which swallow everything nearby, white holes would constantly eject matter into the surrounding universe. However, there's a problem. While black holes are now widely observed and confirmed through astronomical evidence, white holes have never been directly detected. No telescope has ever clearly observed an object behaving like a white hole. This raises an important question. If the equations allow white holes to exist, why have we never seen one? One explanation is that white holes may be extremely unstable. The moment anything from the outside interacts with a white hole, the delicate mathematical structure that allows it to exist could collapse. In other words, white holes might exist only briefly, disappearing almost as soon as they form. Another possibility is that white holes could be connected to black holes through hypothetical structures known as wormholes. Wormholes are theoretical tunnels through space-time that could connect two distant regions of a universe. Some physicists have proposed that matter falling into a black hole might eventually emerge somewhere else through a white hole. In this scenario, the black hole acts as the entrance and the white hole acts as the exit. Matter that disappears into the darkness of the black hole might reappear in another region of space entirely. Although this idea is fascinating, it remains purely theoretical. Wormholes themselves have never been observed, and maintaining a stable wormhole would require exotic forms of matter that may not exist in nature. Even so, the concept of white holes continues to intrigue scientists because it pushes the boundaries of our understanding of time and gravity. In fact, some modern theories suggest that white holes could be connected to the deepest mysteries of black hole physics itself. When matter falls into a black hole, information about that matter appears to vanish from our observable universe. This leads to what physicists call the black hole information paradox. According to quantum mechanics, information should never truly be destroyed, yet black holes seem to erase it. Some theoretical models suggest that white holes might provide a mechanism for that information to eventually escape back into the universe. Recent developments in theoretical physics have revived interest in white holes in unexpected ways. Some researchers studying quantum gravity have proposed that black holes may not last forever. Over incredibly long timescales, Black holes slowly lose mass through a process known as Hawking radiation. This radiation occurs because quantum effects near the event horizon allow tiny amounts of energy to escape. Over billions or even trillions of years, a black hole could gradually shrink as it radiates energy away. But what happens when the black hole becomes extremely small? Some theories suggest that instead of collapsing into nothing, the black hole could undergo a dramatic transformation. In these models, the black hole could bounce and transition into a white hole. The matter that once fell inward would then be released back into the universe. In this view, white holes would not be ancient objects left over from the birth of the universe, but rather the final stage in the life cycle of black holes. If this idea is correct, the universe might eventually contain countless tiny white holes slowly releasing the matter they once consumed. This concept also connects to another cosmic mystery, the origin of the universe itself. Some cosmologists have speculated that the Big Bang might have resembled a gigantic white hole event. Instead of matter collapsing inward, the universe began with matter expanding outward from an extremely dense state. In that sense, the birth of our universe might share certain similarities with the theoretical behavior of white holes. Although this idea remains speculative, it highlights how closely the concept of white holes is tied to fundamental questions about the origin and fate of the cosmos. White holes also appear in certain models of loop quantum gravity, a theory that attempts to unite general relativity with quantum mechanics. In these models, space-time itself has a discrete structure at extremely small scales. When matter collapses into a black hole, quantum effects could eventually halt the collapse before an infinite singularity forms. Instead, the compressed matter could rebound, creating a white hole that releases energy back into space. From an outside observer perspective, this transformation could take billions of years. But from the perspective of the collapsing matter itself, the transition might occur in an instant. Such strange distortions of time are a natural consequence of extreme gravitational environments. Despite these fascinating ideas, white holes remain one of the most mysterious predictions of modern physics. Without observational evidence, scientists cannot confirm whether they truly exist. Yet the concept continues to inspire research because it challenges our understanding of how space, time, and gravity behave under the most extreme conditions. If white holes do exist somewhere in the universe, they would represent one of the most extraordinary phenomena ever discovered. They would reveal that the universe is even stranger than we currently imagine. For now, white holes remain hidden within the mathematics of Einstein's equations, waiting for future discoveries that might reveal whether these cosmic opposites of black holes are real objects or simply elegant solutions within the laws of physics. As our telescopes grow more powerful and our understanding of the universe deepens, we may one day uncover evidence that confirms or rules out the existence of white holes. Until then, they remain one of the most fascinating possibilities in the study of the cosmos.